gamma ray bursts in itself are very interesting phenomena discovered already in 60s. Of course, this is an artistic view of what is happening. We don't have an image of the gamma ray bursts. And maybe you know, but it was discovered sort of by accident because gamma ray satellites were launched by US to check whether Soviet Union does not perform tests of nuclear explosions. And at some point, those satellites, Vela satellites, discovered several such bursts. The first one was on July 2nd. And it looked kind of strange, not like the nuclear bomb, but something else. So the USA did not attack Soviet Union, fortunately, but they started top secret scientific research on that. And after detection of several bursts, which were coming from different parts on the sky, apparently unrelated to Soviet Union, the detection was declassified, and the first paper was published in 1607. Sorry, there is a mistake, I think, because there was several years of between publication and detection. Honestly, now I don't remember whether this date 67 is the date of detection or the date of publication. If somebody has a phone, can check in Wikipedia, I guess. Anyway, sorry for that. But the problem which appeared after the publication was the nature of this phenomenon, because it was just a burst of gamma ray radiation lasting few seconds. That was it. And the determination of the distance is always the most difficult one in astronomy. So before the distance was determined, there were various ideas what it could be. And some people suggested that it was a phenomenon in our solar system. So comets were colliding, and colliding comets led to creation of gamma ray bursts. On the other hand, there were also ideas that it is cosmological, of this phenomenon of cosmological origin, and the first advocate of that was Bogdan Paczyński, because he looked at the light curve and he suggested that it is kind of similar to supernova. But you know, it was not quite clear. Or still in 1995, there was a formal debate between Bogdan Paczyński and Don Lamb, and Paczyński argued for cosmological origin, Lamb argued for phenomena related to neutron stars in our galaxy. And at that time, I think people were divided 50-50. So it was not clear what to do.
I just checked the 1970 is the first discovery.
Is the discovery, and the publication was later.
1973.
Yes, I remember it was several years, which took to declassify. So later in 90s, special satellite was launched, the Compton Gamma Ray Observatory, and it had BATS instrument to detect the gamma ray burst, and that instrument detected 3,000 gamma ray bursts at least. This is taken from Wikipedia. But still, it did not solve the problem of the distance. And the problem of the distance was solved by much smaller satellites, mostly Italian, I think Italian-French satellite, BeppoSAX. Because that satellite had not only a gamma ray detector, that was mostly X-ray detector. But it had also gamma ray detector. So the satellite was small, but still it was sensitive enough to detect one gamma ray burst through its gamma ray detector. And then the satellite was immediately turned towards the right direction. And the X-ray source was detected. And the problem is, the point is that the localization of gamma ray sources, at least at that time, was with accuracy of 1 degree. So in 1 degree, you have enormous amounts of optical sources, everything. You cannot identify the counterpart later. But in the case of X-rays, the detection is much more accurate. It's arc seconds. So then immediately when the detection was made in X-rays, then people turned also optical telescopes in this direction, and they identified the host galaxy. And then having host galaxy, you have emission lines, and having emission lines, you have redshift, right? And then the redshift of the source was 0.695. And the issue was settled. And I don't understand the problem. Why Batse did not solve this problem was kind of political. Some people didn't want to have X-ray satellites accompanying Batse. And they missed the most important discovery in this field. While Batse was much smaller and had both gamma ray and X-ray satellites. So it's really important to do observations multi-band because you have supplementary information. So now, of course, we know that those phenomena are of cosmological origin. On the other hand, they are still divided into two types. And that was noticed by Batse, because if you measure the duration of the flare, gamma ray flare, and you make a histogram, here is the duration, and here is the number of events, you something like two clearly different peaks. So the division was made into short gamma ray bursts of the duration below 2 seconds. This is the dividing line, and long gamma ray bursts of duration longer than 2 seconds. And now we know that, well, they correspond to slightly different physical mechanism, although both are at cosmological distances. So physically, this event is short gamma ray burst is much shorter. It's a fraction of a second, really. So very, very dynamical thing. So then this is interpreted as a coalescence of two neutron stars, or a neutron star and a black hole. And confirmation of this came with detection of gravitational waves. So that was additional confirmation that this is it. And now physically this is sometimes called kilonova event, because it is much brighter than supernova, but well, kilonova. Not less bright than supernova, but more bright than usual nova. On the other hand, long gamma ray bursts, they last more than 2 seconds. Sometimes they last several hundreds of seconds. Their light curves are more, excuse me, still have problems with my throat. Again, light curves are much more complicated, not a single burst. And this is interpreted as a collapse of a massive star ending its evolution. So of course we do not have the image, resolved image of this phenomenon, only, you know, the artistic picture, how it looks like. So first you have 2 neutron stars going around itself. They are not strongly emitting at that time, but they are emitting gravitational waves when they in spiral, and this part is visible in gravitational wave detectors. Finally, the orbit shrinks because the angular momentum and energy, but mostly important, angular momentum is lost by gravitational waves. So then 2 neutron stars merge and a jet forms. And this later is seen first as prompt gamma ray emission, and then slowly as this jet hits the external medium, the reprocessed emission appears both in X-rays, optical, infrared, everywhere. In the case of long gamma ray bursts, also we do not see the stage of the explosion, in the sense of we don't have the map. But it is like a supernova event. So of course we observe supernova remnants. So later on we can even have resolved images, but after waiting for time long enough, the remnant expands and is measurable, visible on the sky. So the phenomenon happens when this massive star, it has to be massive. Massive star finishes the nuclear fuel, everything is already burned. So then the core collapses, forming a black hole of the mass of few solar masses. And then the material partially accretes on this black hole. But everything takes a few seconds. And the mass of the star is, let's say, 40, 50 solar masses, could be more. So the accretion rate is estimated at that stage as 0.1 solar masses per second. So if you try to calculate Eddington ratio, that would be 10 to 13. It's really incredible. So there is a kind of accretion disk which forms here. Oh, this is, of course, again, artistic view. But this accretion rate, this accretion disk is very, very different from the accretion disk we discussed. First and most important difference is that the density in such a disk is comparable to the neutron star density. So the disk cools through neutrino emission, not through photon emission. So it's kind of exotic, but, well, picture could look like this. And then somehow there is a star around it, but, and this envelope actually is ejected, because this is like supernova ejection, right? So you have collapse in the core and ejection of the envelope because of the energy dissipated in this process. And then somehow jet forms and drills through all this material all the way up and outside from the initial engine. So at the beginning, this was a kind of argument that it cannot be like that. It cannot be the proper mechanism because the jet would not be able to drill through all this surrounding material. But the argument of the Paczynski was, well, it's not a problem, it's the problem for the jet, right? And apparently the jet can do it somehow. So as the jet expands and propagates, it hits the interstellar medium. So at the beginning, we see the prompt emission in gamma rays. But then when this expansion of the jet is stopped or slowed down, we see also optical emission from the shocks of this afterglow emission in many wavelengths, including radio, optical, whatever. What is the difference between a gamma ray burst and normal supernova explosion? Honestly, I'm not sure if this is really well understood. Maybe it is that if the jet is not going towards you, you do not see gamma ray emission. And then you miss this interpretation of gamma ray bursts. On the other hand, maybe you need low metallicity surrounding, because then the collapse is more intense and the ejection is less intense, because if you have high metallicity medium, you have high opacity, you have strong radiation pressure, and you eject material more easily. I think statistically also it's not finally determined whether all supernovae are related somehow to gamma ray bursts or not. But at least there are several cases where they are. So you see both gamma ray bursts and then all the signatures of supernova which happened at that location. So the question remains whether indeed it was a jet in this gamma ray emission, or whether it was a spherical emission. Rather, statistics, as I mentioned, suggested that since we don't see always gamma ray bursts with every supernova, then perhaps it was a jet, and then orientation is important. But in general, identification of jets, whether we have a jet or we don't have a jet, is not always simple. On the other hand, this is the most important information which we would like to know. Certainly in the case of gamma ray bursts, when we don't see things immediately. And in AGS, as we already talked a little, and we will talk more, jets are directly observed and they are really spectacular. So we would like to understand what is the mechanism of formation of the jet. So first we need a way to make a clear statement whether we have a jet in a given source or we don't. So sometimes in AGM, the answer to the question is simple. We see the jet, right? We see a well-collimated structure, well resolved. This is jet visible at different scales. This is a compilation of images of a different. This is the smallest scale, 0.8 parsec, and you already see a jet. But here you see a jet with the size of several kiloparsecs, more than the host galaxy. So in the case of AGN, well, you just see a jet, and then you see it even in X-rays or in optical and in radio. This is not always true, not always jet is seen in X-rays or in optical, but in radio, yes, in many AGN, you simply see the jet. So there is no need to have additional tests. So for the jet collimation, this is more difficult to determine because the jet is seen in the projection. But still, if you have a map, like here, for example, this is the same map which was on the previous plot, but slightly expanded. You can try to measure the jet width as a function of the distance from the jet core. And in that case, in this way, partially at least to have a hint where the jet collimation happens. So this is the plot again for M87 from Dolleman et al. 2012. And this is the size of the jet and the distance. So at the beginning here, at 10 Schwarzschild radii, you see that the size of the width of the jet is actually larger than the distance, right? So it's a spot. It's not a narrow jet yet. On the other hand, if you go to those distances, like above 10 to 4 Schwarzschild radii, then the size of the jet is below 10 to 4 significantly. So then the jet is well collimated at those distances, like 10,000 Schwarzschild radii or 1 parsec, more or less. So the jet collimation somehow, at least from this kind of consideration, seems to be slow. So first the outflow is relatively wide, and then the jet is slowly collimated. Sometimes we do not see the jet, but when we do, we get the radio map. This is a giant radio lobes of Fornax A radio galaxy. This is, by the way, a combination of the optical image and radio image. So this yellowish or whatever this color is, orange thing is radio emission, and this blue is optical emission. So you see that radio lobes are much larger than the whole galaxy. And you do not see here a jet. And this was the situation actually at the beginning in 50s, when people started to discover radio galaxies. The resolution at that time was very low, so you never saw the jet, but you saw those gigantic radio lobes. And people estimated that if you request radio emission from those lobes, then those lobes would lose energy, and you have to give a source of energy to those lobes. It was not solved at that time observationally, but Martin Rees already in 76 proposed that some kind of supersonic jet from the accretion disk surrounding a black hole is needed, and this jet should power the lobes. Now we don't have to fantasize, so we can only appreciate that he knew that before we saw it, really. So sometimes really theoretical understanding is first, and then the observational proof of the mechanism. So the prediction by Martin Rees was quite accurate. He even considered the formation of radio lobes, because he considered that at some point the jet starts to be stopped by the surrounding medium, and then this shocked medium is flowing backwards. So this is the head of the jet, and this backflow of shocked gas forms this kind of blobs, which we finally see in projection, right? Sometimes we do not see a continuous jet very well, and this is the case particularly in microquasars. But if we collect radio maps in the course of several years, then we see that initially, for example, we see one spot, and then after a few years, there are actually two spots and a core. This is from the macroquasar, I think GRS 1915. This is the same, but for the Blazar 3C 279. So the maps are from 1992, 94, 96, 98, 6 years. But here on this plot, the separation of the images is plotted in light years, and this is 20, this is 60. So it looks like the motion is 10 times faster than the light speed, right? Because in 6 years, the separation increased by 40 light years. But of course, it is not a kind of miracle. This is a kind of projection and the proof that the motion is really highly relativistic. In the case of microquasar, this jet is also relativistic, and apparent velocity is 1.5 c. Here it's a few times c. Otherwise, microquasars and quasars, I mean, with respect to jet, they look identical. So the central engine apparently looks in the same way, independently from the fact that in a binary system, you have a donor star and the central black hole and an accretion disk, while in AGN, you only have an accretion disk. You don't have the donor star, but apparently it does not matter. So here is an attempt to explain that this highly this superluminal motion is just the effect of projection, because you have actually two blobs which move with relativistic speed, and then you observe those two blobs, and in addition, you observe the position of one of the blob not from the same time as the position of the other blob, because this is additionally the effect of relativistic expansion. If you want to know more, you can find a course given by Mitch Begelman on this issue. Very, very nice. So at least we see that in blazars, this kind of flow, jet flow, is highly super relativistic. In the case of gamma ray burst, this is more difficult because we do not see those blobs. We cannot resolve anything. It's too small at that stage. On the other hand, at least we see something, some kind of argument, both for the existence of the jet and for the fact that the jet is highly relativistic, from the break in the luminosity. So here, this is a kind of schematic view. Here is the brightness and time. And the luminosity decreases, the gamma ray luminosity decreases as a power law, and then all of a sudden you see the change in the slope of this power law. And this is the kind of interpretation that if you have a jet which is narrow, but the motion which is highly relativistic, here Doppler boosting factor is 100, then all emission is boosted. So the observer cannot tell whether he sees a jet or not, because he does not see the whole emission. He sees only a very narrow cone due to relativistic effect. But then when this jet slows down, finally this part of jet which is observed, which emission can reach, is larger and larger. So in this part, we have two compensating phenomena. On one hand, jet slows down, so it loses the luminosity. On the other hand, the angular size increases, and that stops the decrease. Finally, you reach situation when you see the whole jet, and then this jet still slows down, and you don't have this compensating phenomenon here. So the slow down or the decrease in luminosity is more rapid. So this kind of break happens when the jet opening angle is the same as Doppler factor of the jet. So here we cannot tell immediately the value because those two are coupled. We need something else to get it. But still, this is a good argument for the fact that we have jets in gamma ray burst, and then this jet is really ultra relativistic at the very beginning. So we would like to measure independently the Doppler boosting factor and the jet opening angle. This is not quite simple, but at least the Doppler boosting is easy to estimate. Easy. It was estimated already by CP Ran in 1999 in a very elegant way. He actually did not assume we have a jet. He assumed a fireball which is spherically symmetric. But he started to worry, and there were a few others before him, but he did it in the most simple and elegant way. People started to worry that if we have such a high density of photons in such a small volume, because at the beginning the volume is really very small, then photons can collide with other photons, and this would create enormous amount of pairs. And if you have enormous amount of pairs, you finally create something like a black body and not like a power law spectrum. While observationally in gamma ray bursts, we see power law spectrum. So the emission has to be optically thin. So he did an exercise. He calculated the optical depth for photon-photon collision, for photon collisions in this kind of shell using the Thomson cross-section and the total number of photons, and he needed photon density. So the method is actually quite similar, like I used in, I think, lecture 2 for estimation of the variability time scale. So it's kind of analogous. Now you need to estimate this value, the number of photons, but the number of photons can be estimated from the total energy. And if we know the distance, then we can estimate this total energy. If we total energy divide by NEC squared, because this is where percreation would appear, then we will have number of photons. Then the radius, of course, we do not see it, but from the gamma ray burst, we know that the variability timescale can be as short as 10 milliseconds. This is the shortest duration of a gamma ray burst. So then you can calculate the size from the timescale. Size equal timescale time light speed. And then the result is 3,000 kilometers. This is the moment when gamma ray emission was liberated for the first time. So you see, it did not actually happen when very, very close to the newly formed black hole, which is much, much smaller. So he finally got the conclusion from this that this optical death is something like 10 to 13. Enormous. Enormous. So how to get out from this situation? Of course, assuming relativistic expansion. In the formulae I was using during the lecture 1, and here also, there is no relativistic term. Relativistic term enters here. So finally, he added a relativistic term here, which is Doppler factor to the power 4 plus 2 alpha. Alpha is related to the spectral slope, and it would take quite some time to explain why spectral slope appears. But Doppler, the presence of Doppler factor is quite obvious, because if the emission is boosted, then you know, photons do not see other photon somehow, because all photons are sent in very narrow direction. So intuitively, it's kind of obvious that the medium becomes optically thin if all photons are emitted not isotropically, but in one direction and very narrow. So if you add such term, then it's not a problem. You now request that this optical depth is smaller than 1, and then you calculate the Doppler factor. And he calculated the Doppler factor 100 to 1000, which is needed to get what we want. Of course, if we have a jet from the beginning, then we should be a bit more careful in estimating the energy, but more or less it's still correct. So the Doppler factor is very high. But in general, measuring exactly the Doppler factor is not very simple. But some kind of accuracy, I don't know, factor 2 maybe, is possible to achieve. There are various methods, but usually something is required, like if we see blobs, then we can estimate the apparent velocity. But that is combined with viewing angle. So we need something more to get the Doppler factor alone. For example, in this paper, Hodata et al., they used additionally the light curve. They decomposed this light curve into separate flares with exponential time decay. And from that, they calculated something which is the brightness temperature. This is a very strange concept, which I'm never very much at ease with this concept, but this is always used in radio. the point is that they measure the luminosity or the flux at a given wavelength. They know that the emission is optically thin because it is a synchotron, but still they calculate the temperature which would be corresponding to the black body emission. It's kind of formal construction. I don't know whether that has any meaning. I think it's not, but it dates back to the beginning of radio astronomy back in the 50s, and this is how people do things. So they calculated this brightness temperature from this variability, time scale and distance and luminosity, and then they say that they know, don't ask me why, honestly, that this brightness temperature should be 10 to 11. So from that, they calculated the Doppler factor, which is still convolves with the projection effect. And then they use the apparent motion measured through beta to get the intrinsic Doppler factor. So they say it's accuracy of factor 2, whatever. There are other methods based on variability. I'm not sure if they are more accurate than that one. At least they determined the Doppler factor for several sources. So it's not simple, but I think within a factor 2 or a few, you can do it in several sources. By the way, this is the definition of the Doppler factor. If you don't remember velocity, it's here. And here I made a table of the current determination, how it looks like. So in the case of gamma ray bursts, it seems like 100 is the minimum. It could be even few hundreds. So it's really highly relativistic. In blazars, some people would say 10, some people would say 20. I think that's more or less the limit. There is some spread, but that's more or less the right value. On the other hand, if you think about Seyfert galaxies, there is a detection of radio structure, of size of a kiloparsec, even in several Seyfert galaxies, which are radio quiet sources. But there is no evidence for any relativistic motion. It's not a relativistic jet. If it is a jet, then it's not relativistic. In microquasars, well, depends on the stage, because microquasars can show strong evolution. So sometimes they do not show the jet, but they can show the jet with Doppler factor, I think, up to 5. They never go to 20 somehow. So they are less relativistic than AGN. Cataclysmic variables. There was some discussion for jets or whatever, but I think we can safely put here 1, because this is not really relativistic jet. I wouldn't say. There may be some kind of radio detection, but really no evidence for relativistic jet. In the case of tidal disruption events, the first detection was by Swift, and the jet is said to be relativistic, but it's honestly mildly relativistic. So gamma equal 2 corresponds to velocity 0.9. It's pretty fast, that's true, but it's not highly relativistic. Still, it is relativistic. In young stellar objects, in many sources observationally, you see and you resolve the jet. This is not a problem. But the jet is not a fraction of a light speed. The velocity is between 100 and 1,000 kilometers per second, so no relativistic jets. And in ultra-relativistic X-ray sources, they are kind of doing better. The velocity is 0.2 c, but still it cannot be considered as relativistic. I would safely say that if the velocity is above 0.9 c, then you have a relativistic jet. Otherwise, no, it's not relativistic outflow. So what is here interesting is gamma ray bursts. Of course, they do contain black hole. Blazars contain black holes. This contains black holes, microquasar, yes, cataclysmic variables. This is white dwarf inside. This is a black hole. Young stellar object. This is normal star. So you see, in the case of normal stars, you do not have relativistic jets, for sure. On the other hand, if you have a black hole, then you may have a relativistic jet or may not. So then it's not that having a black hole is enough to produce a relativistic jet, because in secret galaxies, you do not see relativistic jets, for example. So it seems that for a relativistic jet, we need indeed a black hole, but it's not enough. What about mechanisms of jet acceleration, right? Because we would like to know what mechanism can drive the jet, but it's much easier to tell what is not working. That was kind of simple. For example, if you look at radio quiet AGN, in some sources, those are normal sources. This is, I think, carbon line, right? You see very nice spectrum. This is a part of the spectrum containing carbon line. 2 examples. But in some other sources, you see a depression, which is separated quite significantly with respect to the rest frame. So you have formation of an emission line, and then you have a wind outflowing towards an observer, which absorbs the line. Those are broad absorption line sources. And this is really, this wind is accelerated by radiation pressure because the absorption, you see the absorption in lines, right? So this is what drives the outflow. On the other hand, the outflow velocities are, in most cases, up to 10,000 kilometers per second, sometimes a bit more than 10,000. So altogether, let's say 0.1 c. This is not relativistic outflow. So in the well-studied case of radiation pressure accelerated outflow, the outflow is not relativistic. That in the case of jet, actually, Marek Sikora did a very nice study already in 1981, Sikora and Wilson. At that time, people in Warsaw, mostly Bogdan Paczynski and collaborators, developed a model which was promising for jet formation, or at least they thought it was promising for jet formation. That was Polish donut or a thick torus. This is the inner part of the thick torus. And then thick torus, in a natural way, has a kind of a funnel. So then the question was, can we accelerate the few protons or electrons which are sitting in this empty funnel by the radiation from the walls of the torus? And this is what Marek Sikora calculated. And he got that in the case of proton, the maximum velocity was only 0.4 c. In the case of pure plasma, he was doing somewhat better, but never above gamma Lorentz factor 3 for pure plasma. Why it did not work? Because you naively can think that you have a proton. Here you have this torus, which is emitting. Most of the energy is dissipated close to the black hole. So most photons are arriving from that side, right? And they should push the proton, right? But the problem is that if proton is accelerated already to significantly to the significant velocity, so the Doppler boosting starts to be important, then there is an aberration for ingoing material. Like now, if you drive the car very fast, then the rain can even go up the window, right? You have the aberration. So then if the proton is moving relativistically, only photons arriving along the symmetry axis, and there are almost no such photons, can push it up, but all the other photons, they appear to this proton as going from the opposite direction. They stop it. And that's it. So you cannot do relativistic acceleration by radiation in a funnel. And this is what Marek showed already many years ago. Forget about radiation pressure acceleration. That's not going to work. So we are left actually with two possibilities. One, and they are both sort of related to magnetic field and sort of related to geometrically thick accretion flow, but rather optically thick than thin. But so one is Blanford and Payne, and one is Blanford Znajek. So in any case, Blanford is right. If you look at the number of citations, Blanford Znajek is slightly winning, but not much. So we cannot be sure which of those two mechanisms are actually working, and they are quite different, or I would say widely different. So in the case of Blanford and Payne, they considered, first of all, an accretion disk which contained the magnetic field. And this is from the presentation of Christian Fend's lecture. But this magnetic field from the disk finally can form a large-scale magnetic field. And if you have large-scale magnetic field and if you have a jet, then it looks like you have a current. And then if you have two lines with the current, they attract each other, and this is the basic part of the jet formation. So those current lines, they attract each other. But here, of course, is a kind of hand waving partially how this large scale structure here formed. So formally, we start from field lines which cross the accretion disk at some angle. And then when the accretion disk rotates, those field lines, they wiggle, and they finally can eject the material, and finally somehow from this part we go to that part. And in this paper they derived kind of self-similar solution for this kind of acceleration. So the self-similar solution somehow represents the final stage of the evolution, because at the beginning we have those frozen magnetic field lines which co-rotate, they then bend. Then also there is a toroidal field, because when they start to bend, the toroidal component forms. And then finally this toroidal component is key importance for the formation of this kind of structure which was shown on the previous page. So this is the self-similar solution from the original paper, which has two parameters. One parameter is angular momentum, and that I'm not sure why it's constant, but this is how it is. It's kind of constant. The other parameter contains the magnetic field. And then overall, the magnetic field is assumed in this model as scaling with the radius, more or less as the radius to the power -1, but they use specifically this. And then many people use this kind of self-similar solution, just borrowing their ideas. What is kind of characteristic, because this is the vertical height and this is the radial distance, all lines bend in this direction, right? Something like that. They are concave. I always confuse concave and convex, but I hope this is concave. Yeah. Okay. This is interesting because all the wind, for example, wind solutions, when winds are powered by radiation pressure, they have the opposite property. They bend in this direction. So in principle, this should help to disentangle at least those two types of winds. Because if you have a cross section and then the observer sees things, different lines, then the velocity system should indicate whether this model is working or in the case of outer wind, radiation-driven wind is working. But it's not yet conclusive even in the case of outflows like warm absorbers or anything like that. So for the jet, yes, well, in this picture, actually jet is a part of a wind, right? There is no essential difference between the jet part and the wind part. But you have this kind of collimated wind, which maybe later requires additional collimation. On the other hand, Blanford Znajek, a few years earlier paper, is based on absolutely different mechanism. We do not start from the accretion disk. At the beginning, we don't need it. We will need it later only to collimate the jet. We start with a rotating black hole. In standard GR, it was proven that the black hole mass, which is not rotating, can only increase. It cannot decrease. Non-rotating black hole always increases its mass. Whatever you do, the mass increases. On the other hand, if you have a Kerr solution, then the mass consists of two parts. One is the irreducible mass, which corresponds to the situation that you take away all the rotational energy from the black hole. So you change black hole, which is rotating, into a black hole, which is non-rotating. And then this irreducible mass is smaller. So in principle, if you have maximally rotating black hole, if you stop it, you can get out almost 30% of the rest mass. It's quite a lot of energy reservoir, but you have to stop black hole rotating. So at the beginning, it was not clear whether this is an attractive option, but then Penrose came with one exemplary idea how you can do Here I have another example of Penrose process. The first idea was that you have an ergosphere, and in the ergosphere, a particle, virtual particle, decays into two particles. And let's say that one of these virtual particles falls into the horizon, and then this one has highly negative energy. So then the other one will be able to escape, and then it will carry energy, positive energy, and angular momentum. So it will escape at the cost of black hole gravitational field. Here is another example, which is more realistic, perhaps. You have a collision of one particle which is entering and the other particle which is moving outward. In ergosphere, it is possible. Only motion has to be in the same direction as the rotation of the black hole, but motion outward is possible. And then as a result of this collision, one particle goes under the horizon with very high negative energy, and then the resulting particle is ejected with much higher energy than it had originally. And in the same way, you gain energy and angular momentum at the expense of black hole mass and rotational parameter. So in principle, this kind of Penrose process can work, but this is not yet jet formation, right? So what Blanford Znajek proposed is not the decay of individual particles, but they said, well, particles are doing something, whatever, and then you have a magnetic field which goes not only through the ergosphere, but even through the black hole horizon, something like that. And then plasma, which is along this, plasma which moves along those field lines can extract. So in a sense, this magnetic field anchors now the black hole into the surrounding accretion flow and then stops rotation. So intuitively, it looks like it could work. On the other hand, it's not obvious whether those field lines really crossing horizon, that's kind of realistic or not, and this aspect is still under discussion. Anyway, in principle, it should be easy to test whether this thing works or not, because Blanford Znajek give the energy extraction efficiency, which depends on the black hole horizon, of course, magnetic field as usually, but it depends on the spin of the black hole, at least as spin square, a square. That means that only highly spinning black holes should be able to produce strong jets. And low spinning black hole, they should not produce strong jets. So, in principle, if we measure this spin, then we could tell whether Blanford Znajek is promising or not. On the other hand, this picture of field lines crossing the horizon is kind of annoying. So finally, they also have another picture which has no such problem, but then field lines are discontinuous. So I'm not sure how it happened, but this is what happened. I'm not saying I understand how this mechanism works, and I think many people have some doubts about it. And I had a pleasure many years ago when that became fashionable. I had a pleasure to ask Roger Blanford, how reliable is this mechanism? And he told me, I don't know, ask Znajek. So on another conference, I asked Znajek, who is actually a Polish guy working in US, and then he told me, ask Blanford. So I don't know if the authors say that they do not fully understand how it works, then the mechanism is difficult. On the other hand, indeed, it gives clear dependence between the power of the jet and the spin of the black hole. The additional problem is that indeed, on one hand, this here highly spinning black hole should be a source of efficient source of energy extraction. On the other hand, for an extreme case of A=1, as many people showed, that indeed the magnetic field is entirely expelled from the horizon. So it goes somehow along the horizon. This is a plot from the paper of Vladimir Kara's cross section in the equatorial plane, and those are magnetic field lines, very complicated structure, whatever, but nothing below the horizon. So if this magnetic field is kind of sliding and not keeping the black hole, then there is no friction. And I talked to Vladimir a lot about it, and he also said that it's very difficult to solve, because one thing is to solve the magnetic field in an empty space and full GR, and this is what he did. And then if you introduce the plasma, then you cannot use ideal MHD approach, and then it's difficult. And then we don't know whether there is a friction or there is no friction. So it would be the best to just measure the spin and then see observationally whether Blanford Znajek is better or not. For the few cases of microquasars, Steiner et al. Compared the Blanford Znajek prediction of jet power as a function of black hole spin for 5 or 6 sources. Here there are several sources. They made 2 plots because they were not able to decide whether the Doppler factor is 2 or 5, but in both cases they seem to be convinced that their result is consistent with Blanford Znajek prediction. But this is only for a few sources. I didn't find anything more recent and more convincing. This seems to be easy to settle in the case of AGN, because we have 2 classes of AGNs, as I mentioned, certainly. About 10% of AGNs are classified as radio load, and they have jets, and some of them they are going towards us, and then we call them blazars. And the remaining part are not radio load. So it's quite tempting to say that those which are radio load, they have highly spinning black holes, and those which are radio quiet, they are not highly spinning. The problem is that we have measurement of the spin only in radio quiet AGNs. This is a table from Reynolds et al. And in most cases, those are all Seyfert galaxies, radio quiet. This spin is quite quite high. In many cases, it's really quite high. On the other hand, as I said, it's not that a high spin is enough to have relativistic jet. It would be much better to measure the spin in blazars, because then if there are blazars which have low spin, then this would question the Blanford Znajek mechanism. The problem is, I even before this lecture, I asked Krishna Levaiko, just in case I missed something, is there any way to measure spin in blazars? And the answer is no. So we cannot test that directly. So the presence of a jet requires additionally, whether Blanford Znajek is working or not, the presence of geometrically thick, could be optically thin flow. That's quite clear from observations, and that is seen in the best way in galactic X-ray novae. We talked about this when we discussed the accretion disk instability, and the ionization instability led to regular outbursts. And I showed even this diagram where here is the X-ray spectrum of the source, and here is the luminosity, and the evolution goes like this. This is a kind of turtle diagram. So first the source is low luminosity hard, and then it has this inner hot flow like ADAF, IRAF, whatever you want to name it. And then at some point it reaches Eddington luminosity more or less, and it goes to the high soft state, and then it goes back, decays to the hard state. This is also related to the presence of the jet. This is a picture from Belloni, maybe Belloni. I forgot to put the name of the author onto that. In that part of the diagram, this is the same diagram, only more artistic. In that part of this diagram, you have a jet. And here is a jet line, and there is no jet here. So when you have this optically thin hot flow, you have a jet. And then at some point here, the source is luminous. So this is the state of the source here, still under discussion whether you already have a Keplerian standard disk here or not. But certainly looking at the spectrum, you have a lot of hot plasma. So at least you have a hot coronal flow on the top of the cold disk. So you have geometrically thick flow. And then you go to the standard Keplerian disk, and then the jet is quenched. So in any case, you need this geometrically thick flow, maybe to collimate the flow. In the case of Blanford Payne, you need it from the beginning, because if you don't have the global magnetic field, you cannot have a jet. And you cannot have a global magnetic field in the case of geometrically thin Keplerian disk. In the case of Blanford Znajek, this relation is not so simple, but perhaps you still need it somehow to collimate this outflow, because Blanford Znajek gives you the source of energy, but not the mechanism of collimation. And perhaps for collimation, you need this external large-scale flow or wind or whatever. It's from Fender, actually. So it seems that the presence of this large-scale magnetic field and consequently geometrically thick flow is really necessary. But this does not solve the problem whether it's Blanford Payne or Blanford Znajek. And in any case, those jets are not very highly relativistic. Because as I mentioned at the beginning, no, this is going to this table. Oops. Here. So the most attractive from the point of view of testing theory are actually blazars and gamma ray bursts. But in none of those, I guess, we measure the black hole spin, although from gravitational waves, perhaps we have some estimates of the final rotation. On the other hand, it's probably kind of obvious that when you merge two neutron stars, you have a lot of angular momentum. So probably the final black hole is spinning. No, from observations, we cannot measure that with the current instruments, sorry, because they see in gravitational waves, they see only this spiraling part. But they do not see the ring down phase because this has too high frequencies for the current detectors. So we have a problem. Still, we have a problem, and I think this is really the most difficult problem at this moment. So we have some basic requirements. Like the large-scale magnetic field. Highly relativistic jets seem to form only in systems with black holes, and that might point towards Blanford Znajek. Because Blanford Payne actually could work equally well in systems with neutron stars, right? While systems with neutron stars, they do not have highly relativistic jets. But it's not yet a strong 100% argument. Again, I asked Krishna Levaiko, and he thinks that it is Blanford Znajek. So if you want to believe him, it is Blanford Znajek, but I think final observational proof is still ahead of us. And it's kind of frustrating, right? Because if you want to measure, to model the system, accretion disk, black hole, jet, wind, everything all in one from one model, if you don't know the source of energy, that's kind of frustrating. Some MHD simulations, they sort of include Blanford Znajek, but it is also in a form of cheating. I'm not sure if you are really interested in this topic. Again, ask Krishna Levaiko, and he mentioned, what's his name, Tchaikovsky. He's doing 3D simulations which can mimic Blanford Znajek. And this is what he gets, that this mimicked Blanford Znajek carries the jet, and the jet lines do not start from the disk, but they do start from the black hole horizon. On the other hand, this boundary condition at the black hole horizon, they are not honest yet. So that's the current state of the situation. No homework unless you want to solve the problem.